So first law of thermodynamics for open system. So far we covered nozzles and diffusers. Then we covered turbines, compressors, and pumps. Right? And last lecture, we started working on throttles and heat exchangers. Right? Heat exchangers closed feed water and open feed water type. What do I mean by closed and open? In closed feed water heat exchanger, two substances at different temperatures don't mix. And they're not mixed. They don't see each other. They only send energy to the wall. Right? That's the closed type. And open pipe, we have one chamber, different inlets and outlets. We mix them. You can either mix one pipe or different pipes. We're gonna only look at one pipe. We don't want to look at chemistry side and etc. We don't want to make it more complicated. Okay, we're gonna just look at one pipe substance coming with multiple inlets or at least multiple inlets and at least one outlet. Mix them and try to satisfy the conditions in the inlet and the outlet. Okay. So open system, they're also called mixing chambers. All right. Open feed water heaters or mixing chambers or open feed water heat exchangers. So it needs to have at least two inlets, might be more, and at least one of them. 1, 2, 3. And from a conservation continuity equation, right? M1 and 2 equals M3. Remember conservation of mass. Mass at the inlet, summation of mass at the inlet minus summation of mass at the outlet equals mass accumulation. Again, we are still continuing on steady state conditions. So right hand side is 0, inlet equals out. Okay. So M1H1 plus M2H2 equals M3H3. How did I get this? From a first law equation, right? Q minus work done, right? But this from a continuity equation, right? M1 plus M2, whatever we have at the inlet, to be equal to the outlet. That's the steady state. Right? And I also know substance at the inlet 1 has some energy, substance at the inlet 2 has some energy. They sum together and get out with a different energy, right? Example. open feed water heater operates at 7 bar. Compressed liquid water at 35 Celsius. Enters at 1 session. The water exits the heater as saturated liquid. Determine the temperature of the steam entering another session if the ratio of the mass flow rate of compressed liquid to superheated vapor is 4.521. That's the ratio. Mixture, one outlet, less. One of them, we know the temperature, it's 35 Celsius. I don't know the temperature here. And I also know the condition outside, that's saturated liquid, right? And pressure is 7 bar. Pressure in open feed water heat exchanger is supposed to be same. Okay? If one of your pressure is different than other, the higher pressure will push out the other, so we won't exceed the mixture. Okay? But pressure has to be same. So we have 7 bar in the system, and we also know mass ratio in net 1 and in net 2 is 4.52. From a conservation of energy, Q minus workshop equals summation mass and energy outlet H out kinetic energy out plus potential energy out minus summation mass at the in H n kinetic energy n potential energy. Kinetic energy, potential energies are negligible. They're not mentioned in the problem. There's no shock in the heat exchanger, and we don't have any heat interaction here from outside. So what I'm left with, right? H M3, H3, okay? equals N1H1 plus N2H2. Right? From a conservation of mass, M1 plus M2 equals M3. Right? So I can replace my M3 with 1 plus M2. And after rearranging this, M3 plus M2 equals M1 over M2 plus 1. I divided both by M2. M3H3, if I substitute this back into my energy equation, H3M divided by M2 minus M1H1 over M2 plus H2. H2 here will be M1 over M2 plus 1 H3 minus M1 over M2 H1. Okay. My H1 from table, because I know the conditions, right? It's a compressed liquid, I know the pressure, I know the temperature. H1 will be 146.7 kilojoules per kilogram. H3 is 697.2 kilojoules per kilogram. I know the condition, I know the pressure, I know the phase, the exit. All right. So H2 from here, right? I have everything I need to find H2. H2 will be M1 over M2 is 4.52 plus 1. H3 is 697.2 kilojoules per kilogram minus 4.52 times 146.7 kilojoules per kilogram. H2 will be 3,185.5 kilojoules per kilogram. This is my enthalpy at exit 2. At exit 2. Seven bar enthalpy 3,185.5 kilojoules per kilogram. You should be able to determine the phase. Okay. After determining that, you go to appropriate table. It's obvious that it's been preheated to you. Right? You go to preheated table and find this enthalpy. It should lie between two temperatures. Now we need to interpolate to find that temperature. Does it lie between two temperatures, or do we have an exact temperature? Okay. So use superheated table, find temperature. Temperature in that tube. Is it? You need to interpolate for it? Okay, you should get 360 cells. All right. That's 7 bars. Any questions about this? Okay. So let's start on another subject. Okay. So far, we have been looking at the problem at a steady state, which means accumulation term is zero, right? The EDT, the MDT, so you don't have any accumulation in the system, but it's steady state. What if it's not steady state? Sometimes you need to deal with unsteady state problems. We have accumulation, rate of energy, rate of mass, changes at time. Right? We don't have constant volume, constant mass, constant energy, change throughout time. So for on steady state case for open system. Okay. So Q minus workshop plus summation net H, kinetic energy N plus potential energy N minus out kinetic energy out plus potential energy out, right, equals dE dt. We don't have that. It's not, this term is not zero now. Okay. Or M in minus M out to dN dt. This term is not zero now. We can make any problem, closed system, open system, unsteady state. We can make piston cylinder assembly by connecting a valve. It will be open system connected to a closed system. It will make it unsteady state. Let's look at an example. might make it clear what I mean by unsteady state. Right. A 0.06 meter cube rigid tank initially contains refrigerant one 34A or R134A at 0.8 megapascal and 100% quality. The tank is connected to a valve to a supply line that carries refrigerant 134A. At 1.2 megapascal. And 36 Celsius. Now the well is open. And the refrigerant is allowed to enter the tank. Right? I'm changing the condition now. I had a condition in the beginning, but I'm providing more changing the condition for releasing. The valve is closed when it is observed that the tank contains saturated liquid at 1.2 megapascal. Asked to determine A, the mass of the refrigerant that has entered the tank. B, amount of heat transfer. is in kilograms. Kilograms. Okay. I will give you a minute to draw schematic. It's only a schematic. What do you understand from the problem? Okay. Please, everyone, try to show the schematic, and I will show you. You can compare it by yourself. Shall we? Okay. We have closed system, right? Here we have a tank. Right? We have a tank. That's how problem starts. We have a tank. We have some substance inside at some condition, pressure, temperature. Could be anything. Right? It's a closed system approach. You can approach any problem from an open system view. Right? That's a general approach. You can apply that first law of thermodynamics, conservation of mass into anything. Right? But in this, we have a tank, which is closed system, right? And it's connected to the supply line. I have a valve here, and it's connected to the supply line. How many of you draw it like that? Close. Doesn't have to be perfect, but this is what it should be. Okay. Now we have the refrigerant here, 134A, right? And we are given the condition. Again, they might tell you different conditions. They might not give you pressure. They might give you temperature, entropy, enthalpy, internal energy. And you need to find the pressure. Right? Same cases. You're still on the same page. Just looking at a different point of view. It's an unsteady state because I'm going to open the valve and add more to change the condition. Maybe in some cases, you release it and you add it from somewhere else. It's like a pool filled with water problem. You can solve it from an open system point of view. You have a mass entering, leaving with a different rate. That's an unsteady state problem. So R represents R134A inside, and I know the volume 0.06 meter cube at 0.8 megapascal. And I also know the saturated vapor. Knowing it's a saturated vapor gives me a lot of information. Right? I don't even need to.
Oh, I was gonna say, you said it was 100% quality.
Sure.
So does that necessarily affect the setup problem, or how would that affect the system if it wasn't 100% quality?
If it's,
It would be saturated.
if it wasn't, so quality factor, remember, quality factor ranges from 0 to 1, right? 0 means 0%, 1 means 100%, right? It's impossible to exceed 100%, right? So 1%, remember the definition of quality factor. It's the friction of vapor versus total mass, right? If it is 100%, which means 100% vapor, which means saturated vapor. Right? You only have a quality factor between saturated liquid and saturated vapor. If you have less than 100%, more than 0%, you have a mixture. Right? If you don't have a quality, you either compressed liquid or superheated. Not applicable in those regions. But they don't have to tell you what the quality is. Sometimes you need to figure that out from the problem, given properties in the problem. Right? Just like I asked in the exam. You knew your only the specific volume and you knew your pressure. That's enough to figure out what you have. Two properties, remember? State statement, state postulate. You know, two properties, you should be able to find out the property. In this case, I do. The properties. I know my pressure, I know my quality factor. That's it. Clear? Another question? Okay. And I also know I have refrigerant 134A running on this line. Flowing. At what condition? 1.2 megapascal at 36 degrees Celsius. Right. I have enough information here too. I should be able to find everything. Okay. Running. Okay. So conservation of mass. I have step 1 here. I have state 1. Let's name it as a state 1. Right? And I take the state to another condition. You can call it state 2. State A to B. I'm not interested in that one, right? So you change the condition. You take this condition from 0.8 megapascal to 1.2 megapascal by adding heat and mass. Right? Previously, we were only adding work and heat. Now we are also adding mass, which carries energy from a different source. Okay? From an external source. Now we are combining two different systems together. Okay? You have an example of assignment about it. All right, from a conservation of mass, right? Summation of N minus summation of F to be equal to accumulation in the system. Right? I have an accumulation here, it's not zero. I'm changing my mass inside that tank, like opening the well. Right? What is it? M in. I can get rid of the summation. I don't want it, right? Minus M out equals control volume, right? Mass accumulated in the control volume. How do I get rid of this time, dt? This guy. How do I get rid of it? Integral, right? By integrating. M in minus M out will give me PM control volume. Now it's not in rate form. It's in kilogram. It's not in rate form anymore. Okay. I will come back to this after. Let's also write our conservation of energy. What is my conservation of energy? Q volume minus shot plus N H N kinetic energy N potential energy N minus out M out H out kinetic energy out potential energy out equals energy accumulation in the system. There is no shock. I can neglect that. It's zero. There is no shock anywhere in the problem. I can also neglect net energy and potential energy. So far, so good, right? Right. So for Q control volume, right? You can either say Q control volume or assume it's an in. Remember, I solved one problem last week. So I picked Q in, but at the end of the solution, I found Q out. Remember, it was minus instead of a plus. Remember that problem? Okay. That's the case. Q in. I think it's a solid assumption because I made an E. I can tell from the problem. But if you're wrong, you will find it at the end. Not a big deal. Or you can continue the Q control volume CV plus summation of mass at inlet times H in minus of mass out H out equals dE dt. Again, you take the integral of this, which breaks into two states. From the integral, you go from one point to another. Right? So Q in plus M in H in minus M out H out equals EQ minus E1. What is E2 minus E1? The stored energy in the system. Remember the definition? Stored energy in the system. What is stored energy? U plus kinetic energy plus potential energy, right? This problem, for this particular problem, I can neglect kinetic and potential energy, right? So it remains Qn plus and NaN plus and RA equals M2U2 and 1U1. So I draw my boundary condition. Boundary. I have mass entering the system. There is nothing leaving. Correct? Right? Any questions on this? Right. Clear that it's in. So I don't have this term. Qn plus MnHn equals M2U2 and times M2U2 minus M1U1. Right? If I go back to my conservation of mass, right? Again, I don't have amount. So whatever Mn is, M n equals M2 M1. Same thing. I have this, and I have this. I'm almost done with it. If you are consistent with what you are doing with all these equations, there's no way you can make a mistake. You know how to replace it. That's another thing. Okay, let's continue. Now I know the relation between Mn and N1 and 2 from a conservation of mass, right? And I also know my conditions inside the tank, which is my state point. Right? And I also know what I'm putting in from the line. And I also know the conditions at the white line in the initial state in the tank. I can find any property I need, enthalpy, internal energy, enthalpy, right? Whatever I need. So in this case, if you go and read, you will find your H1. I will remain this to you. Okay, find this. Find this by yourself. Okay? But the exam, you will need to find all of it. I only check the ones I need because I know what I need. I solve any problem. Okay? But you might need to read all of the properties at once for that state. State 1, state 2, state 3, all of it. Just like I gave you table in the exam, I asked you to fill it up, which was supposed to help you. Okay? So U1, you should have 246.82 kilojoules per kilogram, and specific volume, state 1, is 0.02565 meter cubed per kilogram. H to students, you find this part. U2 116.72 kilojoules per kilogram. Specific volume at state 2 0.0008935 meters cubed per kilogram. Or 0.8935 times 10 minus 3 meters cubed per kilogram. Remember, this saturated wafer, right? And I know this saturated liquid. UN, AN, HN, okay? Find these. 102.34 kilojoules per kilogram. Okay? My first state, my second state, and my supply line. I have everything I need. I need to solve this. Now I can find my mass inside the tank initially. I know my volume. I just read my specific volume on the table, right? I find my mass. 0.06 meters cubed over 0.0256 meters cubed per kilogram. 2.34 kilograms. This is my mass initially inside the tank. But it doesn't stay constant. I add more. And I have this must match this much mass when I'm done with the process after I close my 0.8935 times 10 to minus 3 meters per kilogram. And that's 67.16 kilograms. This is what I found, right? From conservation of mass. Now I can calculate how much mass I put inside. Okay. And N will be so kilogram minus 2.4 kilograms. And N will be 64.82 kilograms. Right? And I also find how much heat enters the system. Q in equals minus M1 H Mn Hn plus M2 U2 minus M1 U1. I know every single of these. find my Q. And if my Q is minus, I guess wrong. I probably did right, but you can choose Q, CD. Let's say, okay? Q enters or leaves my control volume. That's what it means. So Qn, if I plug these numbers, minus 4.82 kilogram, Hn plus 102.34 kilojoules per kilogram, plus and 267.16 kilogram, and U2 116.72 kilojoules per kilogram, minus 2.34 kilogram times you want 246.82 kilojoules per kilogram. Qn from here would be 627 liters. Any questions? It'll be more complicated when we start entropy second law thermodynamics. If you know what entropy is, it's kind of hard to explain. Chapter 4, chapter 5, and chapter 6. If you would like to read what next Tuesday we'll start entropy. Yes. Sure, I was planning on giving another example, but we can. We can, but okay. Same problem, different kind, unsteady state, or different. I was planning on something else, but if you want, I can. I don't think we have enough time. Okay. You have one more example in the assignment. Okay? So work on that and let me know. Okay? I think that will be better. You don't have time to solve unsteady state. Okay. I'm going to solve the count problem, okay, with the steady state. 16 to here. Example. A pump operating at steady state. Draws water from a pond and delivers it through pipe whose exit is 90 feet above. Above the inlet. At the exit, the mass flow rate (10 pounds per second). There is no significant change in water. There's no change in water temperature. Pressure or kinetic energy from inlet to exit. If the power required by the pump is 1.68 horsepower, determine the rate of heat transfer between the pump and its surroundings in horsepower and BTU per minute. You're gonna have a minute to try schematic. So I have a pond, water talk to pond, right? Pump here, and I carry that water somewhere. Its elevation 90 feet. What is it? That is steady state problem. Kinetic energy change, temperature, and pressure change, right? No. Pressure change inside pipe part, negligible. Temperature, pressure, and kinetic energy from inlet to exit are negligible. So M1 equals M2. Right? My conservation mass. So Q is the volume minus workshop. N is N, N, N minus out, M out, H out, S energy out, transport energy out. Right? Kinetic energy difference 0. Simulation is 0. So Q control volume minus work, right? Workshop. I can combine this two because I have the maximum conservation, right? M1, M in equals M out, right? So plus M delta H delta potential energy is equal to 0. This guy is M H2 minus H1 plus G delta Z, Z2 minus Z1, right? Z here is elevation, and I know the delta Z, it's my feet, right? Z plus workshop control volume. Okay. It says that temperature and pressure difference are 0. There's no significant increase, change in temperature and pressure. It means that your property stays constant. Okay? So delta H here is 0. We can also prove that by reading the table. Okay? I will leave that to you. So make sure do all those steps. Okay? What is your, let's say, you assume you have a compressed liquid, right? You have a water. Remember the working principle of pump. Pump only works with incompressible liquids. What is incompressible liquid? It's compressed breathing, right? Compressed liquid. It's incompressible, right? you can read the values. You can read the entropy. If you don't have a significant change, right? Cp delta T is 0. Right? I will leave that to you. Make sure you see it. Right? That might be useful for you. Right? So this term is 0 for this problem. So Q control volume will be work shop minus will be plus. Right. Okay. Doesn't matter. Mass E delta Z. Okay. I know my work. It was 1.8 horsepower minus 1.8 horsepower plus flow rate, mass flow rate is 10 pounds per second. G, if anybody remembers G, right, 32.2 feet per second square. We will also cover this at some point. I mentioned you how to go from meter per second square to 32.2 feet per second square. Just make sure you have it. Okay. And 90 feet. But I need to make a unit conversion here to get a horsepower. Okay. Per second, 2 feet square. Okay. So we need pound force, 1 pound force, 32.2 pound feet per second square. And we also need to convert this to horsepower. And 1 horsepower equals 550 feet pound force per second. Rate of heat transfer will be minus 0.05 horsepower and BTU per minute minus 0.05 horsepower, 2,545 BTU per hour, right? 1 horsepower, 2,545 BTU per hour, and 1 hour. Here, Q control volume is minus 2.12 BTU per minute. It wasn't hard. It was just the unit conversion part. Okay. I wanted to do familiar with the unit conversion. You might use it at some point. Horsepower to BTU, from gravity, meter, British unit, and on. Okay, this is what you have. Make sure you understand all these. Go over it. Work on your assignment alone. You can work with the group as well. You can even copy. But it's good to work alone. And let me know if you have any questions. This is all for today. I'll see you on Tuesday. We will start on chapter 6 on Tuesday, which is second law of thermodynamics. Okay. Have a good one.